So firstly, before we get, let's get started. So firstly, let's talk about what a distribution system is. So when we talk about distribution systems, what I'm talking about here is the part of the power grid that connects customers to the substation. So when I talk about customers, I'm talking about residential homes, commercial homes, some industrial users as well. Customers that are all on the low side of the substation at voltages somewhere between 4 kilovolts and 13 kilovolts. So the distribution system consists of several components. The first, most obvious one being the substation itself, which drops the voltage from transmission levels down to voltages such as 4 kilovolts, 12.47, 13 kilovolts, 25 kV, and so forth that are used to supply customers. The second part, so that's what these parts of the system look like with big transformers and so forth. The next part of the distribution system connects the substations to the customers, and that's what we refer to as feeders. So feeders, the role of the feeder is to transport power from the substation down to customers, and often you'll see anywhere between 1 up to over a dozen feeders that are assigned that exist per substation. Now, the feeders are typically classified into 2 parts. There's the primary part of the feeder, which is the section of the feeder that connects the substation to service transformers. So the small little devices that you'll see that transform power down to houses. And then the second, and the distribution transformers. So the distribution transformers drop the power from 12.47, 13 kilovolt categories down to voltages that are used by the customers, 480 volts or 120 or 240 volts. And then the secondaries are the section of the feeder that connect the distribution transformers to the houses. So when we talk about distribution systems, these are the parts of the electrical grid that we're talking about. And there's other components that exist on the distribution system as well, such as voltage regulator devices, especially in rural areas. There's capacitors that are used for controlling devices that are used for controlling voltage on the distribution feeders as well. There's switches, there's reclosers, lots of protection equipment that exists as well. And all of these devices are used to maintain power quality as you're serving customers from the substation and make sure that you have a sensible supply of power to the consumer. In addition to that, there's a lot of other parts of the distribution system that we'll cover as well. But I think this provides a very basic idea of what part of the power grid we're talking about here. So, now that we're on the same page about what a distribution system means, the problem that we're trying to deal with here is to understand how to model the distribution system. And the reason that this is a problem is because distribution data is actually somewhat difficult to obtain for a number of reasons. The first reason is that utilities own the utility data that they have. And it can be very difficult to obtain that from utilities. In our experience at the National Lab working with many utilities, we've had to have extensive non-disclosure agreements or NDAs with utilities to make sure that we're promising not to disseminate that data or make it public, because utilities are protective of that data. There's protections in place to make sure it doesn't fall into the wrong hands and so forth. And as a result, for researchers such as yourselves at universities or other national labs or anyone in general, it can be very hard to obtain real data to work with. The second problem that we deal with is that it can often be very incomplete. Even utilities don't often have a full mapping of their own distribution system in modeling software that they can simulate. For example, the secondaries that we were talking about are often only represented in GIS formats and not in modeling software tools. So given that that's a very big part of the distribution system and connects the customer, is the part that actually connects to the customers, understandings of what impacts of large amounts of PV is going to be, what demand response program impacts are going to be, and so forth. So not only is it hard to obtain the data, but it can also be incomplete. Another part is that time series data is very difficult to obtain. If there's metered information that the utility is recording, often it's not streamlined with their existing models. So connecting that with the data sets can be difficult. So on top of all of this, there's other problems like comparison of utility studies. So one utility might have a very good data set that they can release to some researchers to do some work on. But if you're working in a different part of the country, it can be difficult to compare the work that you're doing in that section or the utility in a different region of the country to a study that was done previously. The feeders that do exist for public research, like the IEEE 123 bus system or 8500 test system or other feeders that have been released publicly are often single feeders, but which is really good for a lot of research work. But when we're looking to do large scale analysis of distribution systems and understand what the impacts of very big changes to how PV is provided, how demand response can perform, how electric vehicles are going to integrate into the system, working on a single feeder scale is often very difficult. So these are some of the problems that are facing industry at the moment. And what our solution has been is has been championed through the grid data program at ARPA-E. So ARPA-E is a branch of the Department of Energy, United States Department of Energy, and they realized that this is a problem when they were trying to run competitions for comparing different optimal power flow algorithms or comparing different algorithms that might work well both on the transmission and distribution scale. And as part of this grid data program by ARPA-E, our Smart DS project had the solution of building really large scale distribution data sets that are synthetic. That means that they don't look like the actual power lines that you see in reality, but they have the same properties, they have the same characteristics. And if you showed a utility planner one of the Smart DS data sets and didn't tell them where it was from, the idea would be that they could believe that this looked like a real utility system, even though it's not actually what is embedded in any of the geographic locations that we created. So that was our solution to this problem, was to create really large scale, high quality synthetic data sets that we could use to do lots of studies and understand what the impacts of all the changes that are happening to the distribution system at the moment might be without having to access real utility data. So that's kind of the general idea of how we're trying to solve this problem of addressing data sets for distribution systems. So the data sets that we're producing are quite comprehensive and include lots of components that we see in real distribution systems in a way that doesn't exist in existing data sets at the moment. So some of the components that we have include things like substations internals. So what the different banks within a substation are, how they're connected to each other. There's also information that connects those substations together. So we included a sub-transmission network that connects all the substations that we have to a transmission node. Also, by the way, feel free to let me know if you're having data quality issues or anything like that. We also included information about all the secondaries, as I mentioned, which is a very big part of the distribution system, and a lot of diversity in the system. So there's rural configurations, there's urban configurations, there's various voltage classes, so 4 kV, 12.47, 25 kV. There's also different wiring configurations, so delta versus Y configurations. And then on top of that, we also have protection equipment. Like I mentioned before, fuses, reclosers, switches between different feeders are all very important parts of real distribution systems. And those, in addition to voltage regulation equipment, such as regulators and capacitors, are also included in some feeders. Some feeders include that, some feeders don't, depending on what type of design they have. one of the other parts of this is that we're really excited about is very comprehensive time series information. So we included time series information at 15-minute resolution for all the loads that we have. And in addition to just the time series information, we had a breakdown of the different end uses that classify customers as that break down the different components into, for example, heat pumps or fans or plug loads and so forth, so that if they're demand response algorithms that you want to test, you can do them on different components of the load, as opposed to just treating the load as a monolithic source. And on top of that, we outputted all this data in several formats that we can use for modeling. So at the moment, we have OpenDSS and SIME formats that we export the data into, as well as GeoJSON formats if you just want to access the data without having it in a specific format, modeling format. We also included metrics that summarize what the data sets look like, so that if you want to pick out feeders that are specific to what needs you're looking to model, you can do that. And lots of scenarios that represent locations for DEIs, electric vehicles, and so forth. So this is a basket list of all the things that we're including and very excited to share with other people in these data sets. And next, we're going to talk a little bit about data set creation. But I'm happy to pause if there are any questions at this point before I keep on moving. I'm also happy to take, yes.
Yeah. Sorry. Any questions from the audience?
Also happy to take lots of questions at the end as well. So.
Right. Okay, I think we can go ahead. Thank you for the stop.
Yeah, so let's talk about how these data sets were created. So we used a tool through one of our partners, Community University in Spain, that's referred to as a reference network model. And the way that this works is that we input information that we obtained from parcel data that we purchased that specifies where buildings are located. Real buildings are located. So we also augment that with OpenStreetMap data that tells us where the streets are. So as you can see in this figure here, this gives us a whole lot of points of load locations. And then we use some algorithms that our partner MIT came up with to estimate what the loads might be for those parcels based on their category, their size, and some spatial information that they have. So once we had some estimates of peak load for each of these different loads, we could then start to assign them to distribution transformers. The way that our reference network model, or RNN, works is that it would place distribution transformers to serve a certain number of loads. Some loads might have a single transformer, like if it's a very big customer, it might have a single distribution transformer. Some, like residential loads, might have several, there might be several residential customers on a single distribution transformer. And that's part of how our RNN works, is it would decide how that would be done. It would then build out the secondaries that would connect the customers to distribution transformers in a manner that looks similar to how we see existing secondaries in the real world. Once that was done, then substations were created, which are represented by the green triangles here. And then the medium voltage feeder, or the primaries, were added to connect the substations to the distribution transformer. Once that was done, then phasing information was provided. Because as many of you may know, in the United States, there's a lot of single phase parts of the network. So not all of the power lines are three phase coming from the substations to the distribution transformers. Often you'll find single phase laterals that just provide phase A or phase C or something like that. And part of RNN's algorithm decides how to assign the primary feeders as to whether they're three phase or medium voltage, a single phase laterals and so forth. At this point, then power flow is run, and if there are voltage issues on the system, then things like voltage regulators or capacitors are added. There's also extra information that's often provided, such as switches that connect feeders or provide redundancy based on safety requirements. And then once all of that's done, the subtransmission is built to connect the distribution the substations together. In other data sets, in some of our larger data sets, we didn't produce sub-transmission networks. We just had the substations created and then connect them to separate data sets that had full transmission systems built in, such as the synthetic ERCOT data set, which we might talk about later. And then finally, once all of that is done, then a whole bunch of post-processing is done to apply things like the substation terminals that I was talking about that you can see here, apply control settings to capacitors and regulators and so forth, and do a lot of other information, assign a lot of other information such as time series data and so on. So that's kind of the process for how these data sets are built up from the parcel data that we receive. And the equipment that we assign is assigned based on a catalog that we put together based on information that we'd received about real utility system equipment that might be used. So we had information that specified what the transformers look like, what type of line settings are often used, and with that catalog, we assign equipment that we used in these data sets. A big part of this was validation. So we can create these nice data sets using R&M, but if they look nothing like reality, then it's a nice academic exercise. So a big part of the process that we had was to validate it really using real utility data sets. And we approached a bunch of utilities and received some of their electrical information under NDA. So we wouldn't release that data, but we could extract metrics from it to compare against the data sets that we were producing. And we could use this to make sure that not only did the values that we were producing look sensible, but the distribution of properties looked sensible as well. So in this figure, you can see the medium voltage line length is one of the key properties that we use to measure if a data set is looking correct or not. And we wanted to make sure that we had a range of feeder sizes that reflected the reality we saw from the real utility data sets. And we did a bunch of statistical characterization to see if we were capturing the variability that we would see in our synthetic data sets compared to what was in the real world, and came up with a reporting scheme that would cover whether we passed, partial passed or fail on these. And that was really used to reevaluate the R&M algorithms to make sure that we were tweaking it to reflect the kind of realities that we were seeing in real data sets. So that sort of covers the process for how we built the data sets. And now we're going to talk a little bit about what these things that we've been talking about actually look like. So this shows the 4 data sets that we currently have available on AWS for people to download and use. So there's 4 data sets that we produced. One is in Santa Fe in New Mexico, which was our preliminary data set and didn't have any time series data attached to it, just peak planning load. The second data set was in Greensboro, North Carolina, and had over 100,000 customers and reflected feeders over the entire metro area of Greensburg, as well as an industrial section on the side you can see in blue, and a rural area that was to the outskirts of the city. Additionally, we also had a data set we produced in Austin, Texas, that we used as part of a trial T&D co-simulation, where we connected it to a very small transmission system that we could use to demonstrate T&D co-simulations. But our flagship data set that has the most feeders, the most customers, and most diversity is our San Francisco data set, which covers not just San Francisco City itself, but the entire Bay Area, as you can see in the figure here, and extends out into many rural areas that neighbor the Bay Area as well. So the large Bay Area data set contains a lot of diversity. So we've got rural feeders that are at various voltage classes, so 12.47 kV, 25 kV, and we also have diversity in voltages in urban areas. So we've got 12.47 and 4 kilovolt systems, as well as some areas that have delta configurations. There's also different strategies that we used for voltage control. So some areas will only have capacitors, some will have mixed management between capacitors and voltage regulators. Others will just have regulators, typically rural areas. And then we also included some information for a basic network secondary that was based on one of the IEEE test systems in downtown San Francisco. Like I mentioned before, there's really rich time series information that we attach, as well as a lot of scenarios that we've included for DERs, PVs, and so forth. Now, one way that you can access this information is using shapefiles that we've provided. So this defines the layout of what the data sets that we produce look like. So they cover the lines, where they're located, transformers, the phasing, all of that information that was done before post-processing. Now, this isn't very useful for modeling, but it is really useful for visualizing the data sets. And some of the visuals that you can see are shown here that show what the line information looks like in one of the Bay Areas. This is really nice to visualize the data set. And another really nice way to visualize the data set is with the GeoJSON data provided. So all this information and a lot of the parameters that are used for the equipment that we have, such as transformer sizes or line lengths and line equipment and so forth, are all included in GeoJSON format, which for those of you who are familiar with GeoJSON, makes it very easy to parse and extract that information out for things like visualization or just statistics and summary data for what a distribution system might look like. In addition to that, we've also produced data sets in OpenDSS and in SIME. So for those of you who've worked with OpenDSS, OpenDSS is an open source distribution modeling software tool produced by EPRI that has both a graphical user interface and more recently a Python API that allows you to connect to Python and Julia API that allows you to run OpenDSS models with in a programmatic way. So because we produced our data sets in OpenDSS, you can use either the GUI to do your modeling in OpenDSS or connect to it using Python, Julia, or other connections that we have. We also have, we've provided a lot of the information that we produced in ways that are accessible to OpenDSS. So we have time series information that's included in load shapes. And we also structured our OpenDSS datasets in a way that is more accessible for people to use. So rather than including the entire Bay Area dataset, for example, in one file, we've structured our datasets to have regions of which there's 40 in the Bay Area. In the Greensboro dataset, there's 3. There's 6 of those in the Austin dataset, just 1 in Santa Fe. So we have these regions that break things down into different areas of the dataset. Within those regions, there are then substations and then feeders. And the way that we structured it in OpenDSS was to have one master file for a region, if you wanted to run the entire region as is, or if you wanted to, you could run individual substations using master files that were specific to the substation. We also included master files for the feeder. So if you just want to run a single feeder, you can do that in OpenDSS without running the rest of the distribution system. This makes it really useful if you want to do smaller scale analysis rather than running everything together. So that's a quick summary of some of the capabilities that we provide for OpenDSS. We also outputted our distribution systems in SIME. So SIME is a commercial modeling software tool that partnered with us through the project to help validate some of our systems. And we outputted our data sets in formats that can be used and read through the SIME tool. And this is really useful because there's a lot of great capabilities that SIME and other commercial software tools such as Synergy or Windmill have that allow you to visualize the systems that you have, to interact with them a little bit more, to zoom in and visualize things in ways that aren't always provided in OpenDSS, and connect to the powerful models in ways that aren't provided in the shapefiles. So what this means is that you can run time series simulations using SIME. You can run some of the different scenarios that we provided that include solar profiles and so forth in ways that interact with all of SIME's capabilities, output formats, and allow you to visualize what the results of those simulations are in the tool. So as I mentioned a few times in this, time series load profiles are a really big part of this data set. And I just want to talk a little bit more detail about what that means. So the profiles that we've added are from the latest Restock and Comstock data sets. Now these are, again, synthetic time series data sets that NREL has produced as part of another project, but that we utilized here. So Restock and Comstock provide residential and commercial building stock models of that indicate what different household loads might, or building loads might look like. And they break things down by different categories, so by different end uses, so that they detail how much load is being produced by fans, by heating, by cooling, and so forth. And they also have a lot of variety in their data sets. So there's variety in what type of customers are provided in Restock and Comstock. So hospitals, schools, commercial office buildings are all represented as different profiles in Restock and Comstock, and each have their own profiles that reflect the realities of the type of load that they represent. So the load that represents a building that is an office block is very different from the load that represents a residential single family home. And because we have all this diversity in these building models, when we attach them to our data sets, we then have a lot of diversity in the data set loads as well. And it captures some of the types of customers, and especially when you aggregate the loads up, you'll see that a lot of variability happens in a way that wouldn't occur if we were using a single type of load repeated over and over again. So it also reflects weather dependency. So you'll see variation in the loads from summer to winter that reflects heating and cooling loads changing over time. And diversity is provided for different years. So we provided data for 2016 through to 2018, as well as a peak planning scenario, which is a single time point load that reflects the peak planning load. So like I mentioned before, there's a lot of different load categories or load end uses that are provided as part of the data set. So the list that we have is here. There's heating, cooling, lighting, fans, pumps, and for the residential buildings, water systems, refrigeration, motors, plug loads, washers, dryers, and so forth. And the point of all this is it reflects diversity in end uses, and especially if you have algorithms that are designed to provide demand response specifically to cooling, this provides you a mechanism to interact directly with that type of end use. Like I mentioned before, we also have solar load profiles that are provided, and these are taken from the National Solar Radiation Database, or NSRDB, that provide us with diversity in irradiance based on the orientation of the solar panel that might be provided. So if there's different tilts and azimuths you have in a distribution system with lots of PV that's installed, that will be reflected in the type of load generation that you get produced from your different PV panels. And in addition to that, there's also variety in PV management strategies. So there's different fault var or fault watt regulation schemes that could be used. And we've applied volt var and volt watt curves that comply with IEEE 1547 standards into the PV systems that we have that do use volt var or volt watt to manage the generation. In addition to that, there's like I mentioned, there's a variety of different voltage or PV system configurations. There's systems that use volt var and volt watt. There's systems that have fixed power factors at different values. And all this diversity helps to create a system that we think looks more realistic than something that would just have a single type of voltage control strategy used for PV systems. We'll talk a little bit more about the scenarios here, in that there's a lot of diversity in how, in what type of scenarios you can attach to these systems. So the base systems that we've talked about have scenarios that reflect different penetrations of PV and batteries that you can integrate into both the SIME, OpenDSS, and GeoJSON models that we produce. So some of the PV scenarios that we've produced are low, medium, high, extreme, and some of the battery scenarios that we have are low and high battery penetrations. And we've represented those models in OpenDSS, SIME, and in GeoJSON formats. We also include scenarios that reflect penetrations of electric vehicles, of fault locations, of demand response, places where there's demand response, AMI measurements, upgrade locations, and controllable switches. But rather than come up with all the different ways of integrating these into the distribution system, what we've provided is what we call static placements that are just a list, a GeoJSON file with a list of locations where these components are located. So a placement for electric vehicles is defined by a JSON file that lists the load locations where electric vehicles are located. And then if you have your own electric vehicle demand response program, you can just connect it to these locations that we've specified. And the nice thing about this is it provides some standardization. So that if you're doing a study with these data sets and you want to compare to someone else, you can say, we use the medium electric vehicle uptake scenario from SmartDS, and you can compare it to someone else who's done a similar medium scenario of electric vehicles in their study as well. Another thing I wanted to discuss was the power flow metrics, and hopefully this isn't too small to see, but we've included an enormous amount of metrics for each of the feeders that we produced, so that you can filter all the thousands of feeders that we've produced by categories you're interested in. So if you're looking for only underground feeders, then you can filter based on the metrics that we provided to identify which feeders are only underground, or if you're interested in only feeders that are rural, or feeders that have a certain number of nodes, or so forth. You can do filtering based on the metrics that we provided. And that allows you to pick and choose feeders that most represent systems that you're interested in simulating or studying and so forth. One last thing before we get into accessing the data, talking about power flow results. So with the data sets that we produced, we actually ran OpenDSS simulations for every single feeder, substation, and region that we produced. And we did this to make sure that our data sets look sensible and that we have voltage ranges that are within, for the most part, ANSI standards, and that when you're doing simulations, it looks sensible. So as you can see here, the voltage ranges that we have go between 0.91 with a very small number of nodes with that per unit voltage, all the way up to high voltages of 1.06 for our base distribution scenario in 2016. When you then add things like solar PV or batteries or other components that make the system more complex, you'll start to see perhaps more violations. If you have an extreme amount of PV on your system, you'll see a lot of over voltages, for example. But in the base scenarios that we provided, these are all fairly sensible, as you can see in the histograms of voltage we provided as well. So that's a summary of what these data sets are, what they look like. So we have about 20 minutes left, and I'd like to talk a lot about how we access the data. Are there any quick questions that we have before we get into that part of the talk?
All right, any questions from the audience? I have a small question. So when you are dealing with these nice data sets, so we also have data sets in OpenDSS and GridLabD, and we customize the DR penetration, try to make correction. But yes, thank you so much for this data set. So when you are trying to organize this data set, like you will provide access, do you find any trouble that is very difficult when you are formatting the data? Just want to learn some negative story if you have any.
Yeah. So we actually, formatting the data was a really big part of this project. And we actually built a whole tool to help us with the formatting of the data. And it's called the Distribution Transformation Tool, or DITO, as we call it. And
Okay.
we use this to read in all the distribution information from utilities that we received and extract the metrics that we used for validation. We used it to output our SIME models and OpenDSS models. So that's the tool that we use to output all the models that we produced. And it's fairly automated. The processes that we use were fairly automated once we received the data from R&M. We would then read all that into Ditto, process it, do the post-processing to modify the models in memory. And then once those models were in a format that we were happy with and had all the control settings and time series data attached, we would then export it using the export modules in Ditto. So Ditto is an open source tool, and if you Google for NREL Ditto, you can probably find the GitHub repository, and you can download it and use it. There's instructions on how to use it if you want to do conversions of your own from, for example, SIME or Synergy into OpenDSS or GridLabD.
Okay, that's very nice to know. Thank you.
Yeah. All right, so let's get into talking about where you can get this data and stuff. So the main location where we've hosted this is on the Open Energy Data Initiative, or ODI. Now this is a really great resource, not just for hosting the SmartDS data sets, but there's lots of other data and really big data sets that are looked at. NSRDB, National Solar Radiation Database data sets I was talking about before are hosted on here as well. And these are provided in S3 buckets that you can access using the web interface shown here. So if you go to data.openei.org and visit the link S3 viewer, !bucket equals od-data-lake, and then provide the extra parameter of prefix equals SmartDS version 1.0, it'll take you to a place where you can start looking at the data sets or the data that we provided in the data sets. So you can navigate through here, you can find where the OpenDSS data sets are located, where the SIME data sets or GeoJSON files are, and download specific files if you want to. And this is great for navigating the data sets. However, if you want to download the entire region or an entire full data set, which contains terabytes of data in some cases, this is going to be very cumbersome. So what I would recommend doing to access these data sets, if you want to download them or download large regions of them, is to use the AWS CLI. So you can use commands such as this, AWS S3 ls, to list a location, and then this will show you what data is included in this location. In this case, we have for the P1U region in 2016 in the San Francisco data set, the base time series scenario includes several substations, an analysis folder, and some information on subtransmission. And there's a lot of other information that's included in here, like the SmartDS version, the master file if you want to run the entire region, load shape information, bus coordinates, and so forth. If you want to download the data set, you can use an AWS command called cp for copy. So AWS S3 copy, and then the location of the data set that you want to download in S3, the location on your local disk you want to download, and then specify you want it to be downloaded recursively. And the no sign-in request means you don't even need an AWS account to do all of this. So you can do this to download the data sets locally to your machine. I will warn you that these data sets are quite large. So if you try doing it for the base location, you might end up with terabytes of data that you're trying to download. So please be careful when you're choosing what folder you want to download. In addition to that, there's a lot of detailed information that we've included on GitHub as part of a user guide that describes all the things I've been talking about here today, as well as the structure of the information of the data, what you can use to access it, some more detailed information about time series loads, the structure of the data, a whole host of information that's really, really useful as a user guide if you want to start using this data set. So that's a quick summary of how you get to the data sets. So at this point in the talk, I can talk a little bit more about some of the applications of these data sets. But I do want to leave some time for questions if there are some at the end. So I might talk really quickly about some of our combined T&D data sets that we've been working on. So in partnership with Texas A&M University, which you might know has worked extensively on building really large transmission systems, which also was funded originally through the Grid Data Program. We ended up working with them to build a combined transmission and distribution co-simulation data set, where we would produce a distribution data set for the entire ERCOT region, and then connect it to a transmission system that was used to cover that same area. And what this means is then you could use Helix, or the hierarchical, I've forgotten what Helix actually stands for, but use the Helix co-simulation platform to do co-simulation between the full Texas data set for transmission systems and all the thousands of data sets that we would produce in the same way that we did for the SmartDS data sets I was talking about for ERCOT. And this allow you to do co-simulation that would connect transmission systems to distribution systems in a really large test case. So this is something we've produced, we did some testing of, and we're hoping to release the distribution parts of this before too long. There's some tweaks that we want to do to make sure it conforms exactly with what ERCOT historical loads look like. But the transmission version of this is currently available, and you can, if you go to the Texas A&M website, you can download their versions of the synthetic ERCOT data sets. And we've done co-simulation of this, or some parts of this region, because obviously it's very big. We did a lot of co-simulation to test the Austin data set that I was showing before with a synthetic version of a transmission system that is very small that we produced for the area around Austin. And we demonstrated that we could do this where we would run OpenDSS to simulate the distribution systems, and then run PowerWorld to simulate the transmission systems and have them talk to each other and see what interactions you could get as a result of that. There's a lot of other work that I can go to talk about a little bit later that explains some of the modeling we've done for electric vehicles on these data sets, and how we've been able to use smart charging approaches to on the distribution systems that we've created. There's also a lot of work that we did for optimization control systems on these distribution data sets that we used as part of a demonstration that we ran inside the lab for how some optimal control algorithms can be used for distribution systems, and there's lots of other use cases for this as well that I could talk about. But I do want to leave some time for questions and some time to recognize the rest of our team that were involved with this, without which none of this would have been possible. So we don't have many questions. I can go back and talk about some of the use cases a little bit more detail, but happy to open the floor if you have any questions or comments or anything you want to talk about it.
Right. Thank you so much. Yeah, if any of the audience has any question, please feel free to just get unmuted and ask question. Yeah, here I have several questions, but I will wait first to see whether the audience have any. Okay, I will try to start a conversation. So when you talk about the co-simulation in your last part, I know it's very nice, collaborative work between the transmission and distribution, but can you zoom in a little bit more, specifically like how PowerWorld and OpenDSS are exchanging information? For example, we know there are different voltage levels, right? People typically try to normalize the voltage to have the per unit result. So how is the message passed exactly from lower voltage level all the way to the higher voltage level? Can you elaborate?
Yeah, so we separate our data, we separate the transmission and distribution sets entirely when we do this. So we have one model that we run in PowerWorld that's running the transmission system, and lots of systems that are running OpenDSS for distribution. And they're separated, but they're connected at the substation. So we assume in this data set that we didn't have any sub-transmission network. We just had distribution systems that went up to a substation, that was, for example, 69 kilovolts, or the transition from 69 kilovolts down to 12.47, or 125 kilovolts down to 12.47. And that was the interface that we used to do the co-simulation. And the tool we used for that was Helix. Now, what Helix does is it's a big tool that allows you to message between different components. So in Helix, you have these things called federates, which you can use to run simulations in isolation, and then Helix will coordinate how they transfer data between each other. So in Helix, what we would do is we'd have one federate that would run transmission, and then we would have several federates that would run each substation in distribution. And each of those would be running independently of each other. And what would happen is that the transmission system would run, and then it would provide voltages, which would be what was the voltage at the feeder source for each of the substations. And then OpenDSS would run with updated load information that would tell you what the load was doing and so forth. And then when that was finished, each of those OpenDSS simulations would then pass up what the total load would be at the feeder head, that would then get transferred over to the Helix, to the transmission federate through Helix, which would then run its next step, and so on. And then you could step through time with each of these OpenDSS federates running in isolation, aggregating its load up, and so forth. And there's a lot of complexity that we can have with this to make sure that there's convergence between all the different federates that are running distribution and a single transmission federate. That's kind of how we tested it with the Austin data set and the Austin dummy transmission system that we produced.
That's very nice. Yeah, one thing is about the resolution of the data. So in distribution system, we typically are much slower. So is it true that for the transmission grid, let's say distribution grid, you have hourly data, transmission grid, you want to maybe simulate much faster, then you simulate that faster time scale for quite a while, and then try to maybe interact with the distribution, or you are at the same time scale. It's only about the measurements that they are maybe getting the pseudo measurements slower.
So when you talk about
oh,
go ahead.
Yeah, what is the time resolution that you are running? Yeah, for example, is it like a second level, or maybe even faster?
So because the time series data sets that we produced in distribution systems were 15-minute resolution, that was the resolution that we were running this co-simulation for when we did our testing. That said, you might be familiar with Helix being used to do lots more complicated things on transmission scales for fast frequency response or other high time scale resolution components. And the beauty of Helix is that you can have lots of federates that are doing different types of analysis, and they can be running separately from each other. So if you wanted to have a separate federate that could do fast timescale analysis on a transmission system, and then use some of that feedback to influence how you were maybe shedding load or responding to outages and so forth, and have that information get fed back onto the distribution system, you could connect a separate federate into the Helix framework, run it as part of whatever simulation you're trying to do, and have it interact with the distribution systems in that way. So the nice thing about Helix is it does a lot of coordination of timescales. So you can have federates that run at 15-minute resolution, and another one that runs at 1 second resolution, and Helix will manage those different timescales for you and make sure that it all steps through in a sensible type of way, and they communicate the information they need at the timescales that's required.
Okay, all right. Thank you.
Yeah, there's a lot of great presentations on Helix. It's a very great community with a lot of people who are doing lots of great research on it at the moment. So if you're interested, I can put you in contact with people who are more expert on Helix than I am about some of the work they've done.
Yeah, we will create a web page for you, and then there we do want to put necessary information, because many students may not know that platform well enough. So this presentation can be expanded with additional resources. Yeah. Thank you. My last question before I check with the audience and let Qiushi raise more question. is, when we deal with the secondary distribution system, sometimes the utility just give us a map. So in your analysis, is it only the primary? I mean, primary, they typically have the sign model. Yeah. So how do you have secondary exclusively, or secondary it is like depending on the area, like San Francisco, Texas, good areas, bad areas? So
no, that's the beauty of these systems. Because we produce them synthetically, we were able to produce secondaries for all of the data sets that we produced. So every model that we have has secondaries included. There are some models that have just medium voltage loads, or not just medium voltage loads. There are some distribution systems that we have that have loads that are medium voltage. These are typically larger customers. So like a hospital, for example, might be large enough that they're served as a medium voltage customer rather than something that's below a transformer. But aside from these medium voltage loads, of which there's some, but not a huge amount, all of our data sets have secondaries. So if you look at any residential data set that we produce, where there's homes, all of them will have secondaries that connect the customer to the distribution transformer. And that we're able to do that because we produce these synthetically. We don't have to worry about what data actually exists there.
Yeah. So how do you create synthetic one? To me, let's say there's a secondary that is with 20 houses, and my house is one of them, right? We typically need to look into how the lines are going further away or be very close, depending on maybe how long they are. We try to assign some impedance or whatever there. So for you, do you do it like a maybe database that you have 1,000 candidates? So any location you try to plug randomly one maybe secondary onto your primary. So how do you create a synthetic one? Because it's so huge.
Yeah,
I'm talking about the diversity. Yeah.
So we used R&M to do this, and we integrated a lot of strategies into how R&M would produce secondary. So we had some fixed limits that said you can't have a secondary that's greater than a certain length, and you can't have and you want to have some preference in terms of how radial your structure looks like, or how many what kind of tree structure your secondary looks like, and whether there's branches that come off secondary laterals, I guess you would call them, or if it's just a pure radial structure, depending on what type of area you are, how dense the buildings were, and so forth. And we were fortunate as part of the validation process to receive some real secondary information from a couple of our utility partners. And we passed that data and extracted some metrics and statistics from that to help inform how we built in our secondary generation process into R&M.
I see.
Yeah.
Okay.
But all of this was synthetic.
Yeah, that's very nice. Okay, for the audience, do you have any question? Feel free to unmute. Yeah, otherwise, Qiushi can take over. Oh, Max, do you have a question here?
Hey,
yeah.
So yeah, I have a question. And by the way, great talk and lots of information in there. So you said something about running the optimization algorithms. Could you briefly tell what kind of algorithms did you learn? Were they like mostly OPF, and were you also looking at all these distributed algorithms, or were mostly centralized and all those things?
Yeah, so this was work that I actually didn't do myself. This is stuff that other people took these data sets and worked with at NREL. But my understanding of this is that what they had done is taken an optimal power flow algorithm and apply it in a distributed fashion, so that you could have small parts of the distribution system that would run in an autonomous optimal power flow, and then have them connect to each other so that you could have them make sense from each of their separate perspectives. So the idea of this was that if you wanted to have autonomous control of your distribution system in different areas of the distribution system, they could run separately from each other, each of which is running their own OPF algorithm, and make sure that each of them is conformed to work together correctly with the OPF solutions so that you don't have them coming up with solutions that don't match when you try connecting them all together. That's my brief summary of this, but I can definitely put you in touch with Ben Kropowski, or who is the lead of this, and also there were a couple other people I've forgotten the names exactly who were involved in this research, and I can put you in touch with those if you're interested in seeing it, because they've written papers on some of these algorithms that they provided.
And all this was in OpenDSS, right? Did you use some other platform to run this?
I think they used the OpenDSS datasets to do this, and then extracted the Y matrix from OpenDSS, and then did the decomposition that they needed to from that Y matrix. But I could honestly, my contribution to this was, here are the datasets. You can use them and come up with these algorithms and stuff on those datasets and making sure they're working correctly.
Yeah, and all the things that you presented today, is this like in a report format on the GitHub? I don't know if it was a GitHub link or the link. Is it documented somewhere too, or because it's lots of information and easy to follow?
This one here. So if you go to this link here, github.com/openedi/documentation tree main smartTS. This is where this documentation is provided, and the documentation focuses on the data sets. I didn't talk too much about the use cases like the EV charging use case or the distributed OPF stuff that was done. The focus is just on the data sets, what they look like, how to use them. But if you want to come up with your own algorithms and so forth that use these data sets, I'd be happy to hear about them and let other people know about it too.
Yeah, sure thing. I'll be in touch. Thank you.
Yeah.
Right, Brian, yeah, you can print screen so that you have this link. At the same time, yeah, feel free to shoot me or Cho's email. I will connect you with Tarek. You can also Google Tarek's name, so online and get in touch with him. But we will build a website and we will detail what Tarek said today. Do you have any other question? Very nice question. Any more?
Thank you. Yeah.
You're good. All right. Okay. Yeah. Any other questions from the audience? All right, Chelsea, maybe you can ask your questions.
Yeah, sure. I do collected several questions from the audience. First, so are there any data for specific load or generation? So, for example, CHP, PV, wind, battery, and so on.
So the data that we produced, we didn't produce any wind data sets as part of this. Although if you are interested in accessing wind data sets, the wind toolkit, I think it's called, contain. I have to look up the link for that. But there is information online that describes wind resources that you can use. The resources that we focused on here were more distribution focused, I guess. So like solar radiation data sets, and the solar data sets that we included here are pulled out from NSIDB and then included in the resources that you can find here. So if you download the data set, you can also download solar profiles that you can connect to OpenDSS or run your own processes with separately. So the solar ones are provided. Other ones that we haven't included in this data set. Although maybe in future versions we could look at doing CHP or other types of profiles as well. Does that kind of answer your question a little bit?
Yes, but how about the load data? So what kind of load types are mentioned, like in terms of data?
Yeah, so the way that we've produced our load is in Parquet form. So the Parquet files that we've produced are located, I guess I could probably bring it up, but the way that the Parquet, the data we produce is located is in Parquet files. So Parquet files is like a compressed format that includes lots of different columns in kind of like a data frame that's to a format that you can then download. So in the Parquet file, you'll have a column for each of these different types. So you'll be able to extract the total site electricity or in kilowatts in kVAR, as well as the different end uses. And then for OpenDSS simulations, we took at just the total site electricity kilowatts and kVARs and produced them in CSV files that OpenDSS can then point to and then use. So that's how the data set loads were produced, and they're located in one of the folders in the repositories that we've created that you can access. Now, the way that each of our loads references those is to, in OpenDSS, for example, there's the load shapes file, and the load shapes file includes a reference to the load shape location using the name of one of the load shapes that's included. So that's kind of the link between the loads and the time series data sets that we're using. Does that make sense?
Yeah, and I feel the load data are more centered for households, right? So are there any industrial load?
Yes. So
yes,
the loads that we produced were from Resstock and Comstock. So Resstock provided the residential loads, and Comstock provided the commercial loads. So the commercial loads are cover various categories. So there's restaurants, hospitals, schools, warehouses, office blocks. There are a lot of different categories that we use. And depending on the building type that's provided to us from the parcel data that we obtained, we know if a certain parcel is a school or a hospital and so forth. And then we would attach those profiles in a corresponding way.
Oh, that's good. Yeah, you can. Yeah, you have like a REST and the Comstock data. Yeah, that's good. Yeah, so people can do a lot of work out of that. So yeah, the next question. What's the motivation of open sourcing this data set? Is there any further funding for you to maintain those data sets?
So the motivation is so that people like you guys can use it. We want, like I said at the beginning, there's a problem with having good large-scale distribution data. It's difficult to obtain. It's often spotty, even when you do get it under NDA. So the idea of this is to have a really clean, really accessible data set that people could do studies with and then compare their work to each other in a way that isn't really possible if you're doing it on one utility versus another utility. So that's kind of why we want to open source it. And the maintenance of it is a good question. At the moment, we just released version 1.0. The funding for it was through RPE's grid data program, which is now finished, but we've got the data sets produced. There has been a lot of interest in expanding these data sets from other programs. So we have had a lot of discussions, and some projects have started, although we're seeing how that's going to progress with other Department of Energy funding sources that are interested in expanding these data sets across the US and perhaps providing more interactability between what a real utility data set looks like, or no, what the real utility information is in a specific location. So for example, if PG&E in the Bay Area has a certain way of building their data sets, maybe most of it is underground or certain areas of it are a certain voltage category, there was some interest in taking that type of information and then using it to inform the R&M creation process more directly, so that we were reflecting what PG&E's system actually was. So there's a lot of interest in expanding it, but at the moment, the funding source that we used to create these has finished, and we're sort of in the disseminating phase of the project at this point.
Yeah, good to know that. Yeah. Talking about the expansion of the data, I also noticed that the title is like realistic but not real. So why not real data? Why isn't real data included?
Well, I mean, there's a lot of reasons that it's difficult to include real data. Like the utilities have their data, protect their data under NDAs typically, where it's not possible to publish it to publicly for anyone to access. And like one of the questions was mentioning before, often utilities don't have good information of their systems. Like the secondary data that we produce, utilities often don't have models of that. They might have a sign model that covers just the primary part of the network, but not the secondary itself. So that's kind of the motivation for why we wanted to create this synthetic approach that's very clean, that we can disseminate very easily. That said, as part of this ongoing discussion that we've been having with some other Department of Energy people, there was interest in having some kind of hybrid type of data sets where if there was really good utility information, maybe we could augment it with synthetic ones in areas that there wasn't. These are all ideas, future research at the moment, but I guess because of the spottiness of distribution data at the moment and how difficult it is and how often it isn't clean, or there might be bad parts of the network, not just in secondaries, but on the primaries. So having something that's clean, that you don't have to worry about data integrity or any of that, just makes everything so much easier for people who just want to do research on algorithms or demand response or state estimation and things like that.
I see. And the last question, I think is important. So for synthetic data, are they repeatable? I mean, after having those data, there are some system parameters I can repeat, and I can do the simulation by myself, repeat the data. Is that possible?
Are you talking about repeatability of creation of the data sets or of simulation of data sets?
I think it's like simulation, yeah.
Yes, well, I mean, the data sets are provided in OpenDSS and SIME and so forth. So if you run OpenDSS with it once, and then if you run it again, you'll get the same results. So, and because it's open, it's an open data set.
So data with the system, with the project file.
Sorry,
so it's a data with project document.
I guess yes. Yeah. So there's not only the data that was generated. Tarak is also saying that they provide the OpenDSS file that you can run by yourself, and then you can see them again.
Yes. We did run OpenDSS with the data sets that we produced. So all the results for a specific time point are actually included in the data sets too. So if you want to look at the analysis of the peak time point that we ran, you can. And yeah, in terms of repeatability, I guess if you take the data sets and run them again, you should get the same results.
Yeah.
Really hope so. But that's that if you run it at the same time point, you should get the same results. But we only ran, when we were doing our testing, we ran it to the peak loading point. And you can run it for lots of other time points as well and get very different results too, based on what the load is at that time point.
Okay, that's great. Yeah, and thanks, Tarak. And that's all from my side.
Yeah, thanks.
Yeah, so So before I give the conclusive questions, is there any other question from the audience? Very nice discussion, by the way. All right, I'm going to have some conclusive questions. So the first one is about the PV. So your video today will be broadcast onto YouTube, and we will build dedicated website to broadcast the information. We will also put your information onto the Big Data Subcommittee website front page, so that people get attraction to this effort by Unreal. Hopefully, many people will continue this wonderful work. One specific question is, many people are very interested in the distribution grid because of DER. yeah, you mentioned that in the Bay Area, there are some like EV data. So, but you know, like what Chosu was asking, it's real, but not real. So for those PV data, so is it like you first get the real data there, and then you try to filter in some sense, and then in the end, you plug them as a load or as a generator onto your secondary distribution system or primary. Can you say more about the electrical vehicle part?
Yeah, so let me talk a little bit about the PV part, because
Okay, yeah, sure.
The electric vehicle, the way we did electric vehicles. So when we created these scenarios, at least this iteration of the data set, we didn't use actual information from the Bay Area about location of electric vehicles or location of PVs to create these. The process to produce these was fairly simple, honestly. We had some low, medium, high, and extreme scenarios that would build off of each other, and they were placed somewhat randomly on the distribution system, with limits as to how much PV could be placed on any feeder based on what the scenario was. And if you go through the documentation, there's a lot more detail that describes what the constraints are for placing PV and so forth on the distribution system, and how those were created. But they're essentially randomly located on the distribution system with some limits, so that you don't exceed the total loading of the feeder under low or medium loading scenario or PV scenarios. And the way that we did that is we would then create a PV object which would attach to that location, and that PV object would be represented by a PV system in OpenDSS or the corresponding one in SIME, that you could then run power flow simulations with, which would be generating power based on irradiance and feeding that into the system and so on. So that's the PVs. But the electric vehicles, we have no electric vehicle generation or consumption models that we attach to this. The only thing that we do is we create a scenario JSON file that says where the electric vehicles are located, and that's it.
Okay.
There's no charging model, there's nothing, no loads or anything like that. Because we understand that there's a lot of complexity and different charging models and so forth. We didn't want to go and presume what all that was. This is kind of enabling people to do their own charging with that.
All right.
Now, potentially in future versions of the model, we could include more sophisticated decisions about where PVs are placed based on uptake models and things like that. But at the moment, we used a very simple approach to decide where the PVs were located.
Okay, all right, that's a very nice answer. So yeah, finally, I want to know, yeah, you work in this field for many years, and there are many students who is going to watch your video. And so basically the next generation of, I don't know, big data for power education. So do you have any guidance to them? Yeah, for example, when they look into your data set, and do you want them to expand such an effort in any way? Or do you have any specific question? You say, oh, it's very interesting for the student to start maybe analyzing a small power flow in the Texas region, which has a very strong interaction between, I don't know, two regions. Do you have any visual suggestions, guidance for the student community?
So that's a really great question.
I know it's broad.
I guess, no, it's good. I like it. I guess the guidance I would have is that a lot of times historically, people would focus on a single feeder and say that here's one feeder. This is what is going to happen if there's a lot of PV. There's going to be backflows. This is how you could do volt var on a specific feeder, and everything was very localized to a specific feeder. And I guess the idea behind these data sets is to encourage people to look beyond single locations of feeders, because with a lot of the push to electrification and especially the movement by often entire cities to get to renewable energy targets and so forth, focusing on a single feeder is very valuable, especially to understand the intricacies of things. But when you're trying to decarbonize or electrify entire cities, expanding on single feeder models is really important for the utility to understand what's going to happen. And the idea of these models is to help people to create the tools that can then be applied to real systems, so that when a city does decide to electrify, you can take the approaches that you've applied to these data sets and use them in reality. That's the motivation behind this. And I think keeping that in mind and trying to push the boundary of how you can do that is really the motivation of this data set, and to encourage you guys to develop the tools that are going to be used for those purposes. And there's a lot of changes in philosophy and thinking that have to happen when you start to scale up, so that, because you can't often get into the weeds of understanding how each feeder works in great detail. You have to be able to extract the relevant information that you need from all the feeders and collect summary information that you can disseminate on a larger scale, with the confidence that when you're running the models that you have on each of your feeders, that they're working correctly using the aggregate information that you've collected up. I guess that's probably the advice that I would have for how to use these data sets, and to really try to push the boundaries and make an impact on the distribution infrastructure, the real distribution infrastructure, using tools that you can apply to these. That's, I guess, my take on it.
Yeah, that's wonderful, and I like it a lot, because I'm also practicing this like analysis in the distribution system. Thank you so much, Tarek.
Yeah, thank you. Great questions.
Right. So yeah, we will summarize the Q&A, and also we want to have a list for students to enter this domain so that they know what are the big names talking about, what they should do, what they should not do, what are interesting, what are not interesting. So that those are upcoming events for our series. All right, then, I would like to, on behalf of the whole subcommittee, I would like to thank Tarek for this wonderful presentation. And we will build a website and follow up with Tarek to broadcast the information from Unreal to the rest of the world. So Tarek, thanks again. And thank you everybody for attending. Appreciate your time.
Thank you, Tarek.
Yeah, thank you, Joseph.
Thank you.
Thank you.